Self-organizing maps. Introduction to self-organizing maps, SOMs. Self-organizing maps, SOMs, are a special type of artificial neural network mainly used for clustering and visualizing large sets of data. They help us understand complex information by organizing it in a simpler way. SOMs were developed by Théo Cohn, so they are also commonly called Cohn networks. Unlike other neural networks that need labeled data, like supervised learning, SOMs use unsupervised learning. This means the network learns patterns and relationships in data on its own, without being told the correct answers. SOMs work by transforming high-dimensional data with many features, into a 2D or 3D grid map. This transformation helps us easily visualize and analyze hidden patterns within complex datasets. Because of this ability, SOMs are very useful for clustering similar data points, analyzing large datasets, reducing dimensionality, understanding relationships between data items. They are used in fields like image recognition, speech recognition, biology, market research, and data mining. A self-organizing map is a neural network model that organizes and clusters data based on similarity. It uses a grid of neurons, nodes, where each neuron represents a pattern in the dataset. Every neuron has a weight vector, which has the same number of features as the input data. When an input is given, the SOM finds the neuron whose weights are closest to the input using Euclidean distance. This neuron is called the best matching unit, BMU. The BMU and its neighboring neurons update their weights to become more similar to the input. Because of this, the SOM preserves topology, meaning similar data points end up near each other on the map, while different ones are placed farther apart. SOMs are widely used for clustering, visualization, dimensionality reduction, and understanding hidden patterns in large datasets. Applications of self-organizing map. Data mining, clustering similar data points for market research or customer profiling. Exploratory data analysis, visualizing relationships in high-dimensional datasets. Image processing, classifying and recognizing patterns in visual data. Text and document clustering, grouping similar documents in information retrieval systems. Anomaly detection, identifying unusual patterns or deviations in network traffic or financial transactions. Numerical example. In the first step of training a self-organizing map, we create a 2D grid of neurons, such as a 2x2 or 3x3 grid. Each neuron has a weight vector with the same number of dimensions as the input data. Given the input vectors, x is equal to 0.2, 0.6, 0.8, 0.4, 0.5, 0.9, 0.3, 0.7. Each neuron will have two weight values, because each input has two components. At the start, these weights are initialized randomly, since the network has not learned anything yet. This provides a basic starting point for the learning process. Now we begin training the self-organizing map using the first input vector, 0.2, 0.6. The goal of this step is to find the best matching unit, also called the BMU. To do this, we calculate the Euclidean distance between the input vector and the weight vector of each neuron in the grid. The Euclidean distance formula is. We apply this formula to every neuron and compare the results. The neuron with the smallest distance value is selected as the best matching unit. After calculating the distances, we find that the neuron at position 0, 0 has the smallest distance, which is 0.141. Therefore, 0, 0 is the BMU for this input vector. After finding the best matching unit at position 0, 0, the next step is to update its weight vector so it moves closer to the input. We use the weight update rule. New weight is equal to old weight plus learning rate times input old weight. Here, old weight is equal to 0.1, 0.5. Input vector is equal to 0.2, 0.6. Learning rate is equal to 0.5. Therefore, the updated weight vector of the BMU becomes 0.15, 0.55. This adjustment pulls the neuron closer to the input vector, allowing the self-organizing map to gradually learn patterns in the data. After updating the weight of the best matching unit, we also update the weights of its neighboring neurons. We use a neighborhood function, such as a Gaussian function, which decides how strongly nearby neurons should be adjusted. In this example, only the directly adjacent neuron at position 0, 1 is affected. We apply the same weight update rule. New weight is equal to old weight plus learning rate times input old weight. For the neuron at 0, 1, old weight is equal to 0.3, 0.8. Input vector is equal to 0.2, 0.6. Learning rate is equal to 0.5. Therefore, the updated weight for the neighboring neuron becomes 0.25, 0.7. The remaining neurons at positions 1, 0 and 1, 1 are outside the immediate neighborhood, so their weights stay the same and are not updated during this step. Step 3. Iterate. Repeat the process for each input vector in the dataset. Reduce the learning rate and neighborhood size over iterations to fine-tune the weights gradually. Step 4. Final sum. After several iterations, epochs, the neuron's weights will be adjusted to reflect the patterns in the input data. Each neuron will represent a cluster of similar input vectors. Updated weight summary after one iteration with first input. Step 5. Advantages and disadvantages recap. Advantages. Clusters high-dimensional data into visually interpretable groups. Preserves topology, showing relationships between clusters. Useful in exploratory data analysis and data visualization. Disadvantages. Sensitive to initialization and parameter settings. May require many iterations for convergence, especially for large datasets. Can get stuck in local minima.